So my name is Spaldin1. I'm the professor for materials theory at the ETH in Zurich, and I actually prepared this much more like a class than like a research lecture. So yeah, I hope that's okay. So the goals of my the sessions we'll have together today and tomorrow. Today we're going to focus on multiferroics, and hopefully by the time we go for lunch, you'll all understand why things that are ferroelectric tend not to be magnetic, and the other way around. That's my main goal, to understand all of the reasons why it's difficult to combine ferroelectricity and magnetism, why it's difficult to make a multiferroic. And we'll go through together the physics that allows ferroelectricity to be combined with magnetism, hopefully to give you the skills to be able to go home and design your own multiferroics after this session. And then next time, depending on how we go for timing, I'll talk about magnetoelectrics, and we'll do a little bit of history and definition. You'll be able to explain the history and the definition of the magnetoelectric effect. And you'll be able to propose ways how, with an electric field, you'll be able to change the magnetic properties of materials. So that's the plan. How many of you are actually working on your research projects on multiferroics or mostly related materials? Okay, so for you this will be, I think, very much a review. Hopefully I'll give you a little bit of a different, maybe a little more chemically perspective than you're used to. And if not, you can go out and enjoy the sunshine. We'll do a little bit of enjoying the sunshine also during the talk. Okay, so first the definition. So a multiferroic is defined to be a material that combines in the same phase two or more of the primary ferroic order parameters. And so it can be ferromagnetic. So it can have a spontaneous magnetization that's switchable by an applied magnetic field. This is the primary magnetic ferroic ordering. A spontaneous electric polarization that's switchable by an applied electric field, so a spontaneous dipole moment in the material. And or a spontaneous deformation that's switchable by an applied stress. And so you all know already from this morning that multiferroics are not at all unusual. Most ferroelectric materials in their ferroelectric state, when they have their spontaneous dipole moment, also have a deformation associated with the formation of the dipole, so they're simultaneously ferroelastic. And so multiferroics that are ferroelectric and ferroelastic are not at all unusual. And likewise, many ferromagnets have a spontaneous deformation associated with the formation of the magnetic state, and so multiferroics that are ferromagnetic and ferroelastic are also not so unusual. But the class that I think are still perhaps the most interesting, and when one says multiferroics, one often thinks about this particular combination are multiferroics that are simultaneously ferroelectric and ferromagnetic. And these sometimes are called the magnetoelectric multiferroics. So these are the ones that are also the ones that are most difficult to make. Questions so far? Sorry, this is just an excuse to drink some coffee. I couldn't get my coffee because I didn't have a glass, and the kitchen didn't have any glasses either, so it took a while. Okay. So why are multiferroics interesting? Well, I said the main reason, or the main technological driver, is because of the crosstalk. If you have a material that's ferroelectric and ferromagnetic, then by symmetry, it can have what's called a magnetoelectric response. So with an electric field, you can modify the magnetic properties, and with a magnetic field, you can modify the electric polarization. Does somebody have a pointer that, by any chance? I think we might, if I would use that one, I'll probably switch off the projector. Don't. So the electric field control of magnetism was originally the main kind of technology driver. Do you have one? You have? Oh, thanks a lot.
Oh, great. On a screen.
Thank you very much.
I think I need to put this one.
And so certainly when we started working in the field of multiferroics, the idea is that if we could control magnetic properties with an electric field in terms of technologies, this would be very valuable. Recently, there's become more interest in the opposite coupling, magnetic field control of electrical or structural properties. And I'd say this is still very long range, but for biological applications, if you can implant a device and control it magnetically, this can be done remotely, so you don't need electrodes, and so this is desirable for in vivo applications. And then also, of course, they're very interesting because they're so rare. Okay, so what I want you to do now in groups of 5, I think we should all go outside for 10 minutes because it's so stuffy in here. I want you to write down, make a list in your groups of 5 people, your favorite ferromagnetic materials, and a list of your favorite ferroelectric materials. And I want you to look at those and see what's different about them. So we can think about why magnetic materials tend not to be ferroelectric and ferroelectric materials tend not to be magnetic. And in your groups, you may not have 2 people from the same institution, and you should try to find someone you've not spoken to yet on this. Is there anybody that you've not spoken to yet in this workshop, or do you all know each other?
We all know each other.
You all know each other, okay. Then groups of 5 people, but nobody from your own institution, and preferably people who you haven't spoken to yet. Okay, so 10 minutes, everybody out there. So I had some discussion. One was that most ferroelectrics are oxides. Not all. I noticed nobody put germanium telluride. Does no one have germanium telluride? Is that this is your work on oxides. Mostly oxides. Ferromagnets are mostly not. The magnetic ones on the list there are mostly ferrimagnets, right? Where the interaction between the moments is anti-parallel, but they are in balance. So this is one thing I heard people discussing. I heard one group discussing that ferroelectrics, of course, have to be insulators, whereas ferromagnets are mostly metals. So this is a problem. Of course, if I have a metal, I can't be ferroelectric because I can't sustain an electric polarization. When I apply an electric field to a metal, it conducts electricity. I don't reverse the electric polarization. Can you read my handwriting at the back? Is it large enough? Another one I heard is a question of symmetry. Most ferromagnets have an inversion center. They're mostly centrosymmetric. If you look at the crystal structures, they're mostly, for iron, for example, it's cubic, right? And a ferroelectric has to not have an inversion center. You can't have a, you have to break inversion symmetry to be ferroelectric. One group was discussing, already wrote this up. If you look at all of your ferroelectrics, the transition metals have, apart from the multiferroic ones, the ones where we solved the problem of making the magnetic and ferroelectric, the transition metal, the formal charge of the transition metal, has empty d electrons. So for example, titanium 4+, there's no d electrons. Niobium 5+, there's no d electrons. Whereas to be magnetic, we need some source of localized electrons, which in a transition metal is the d electrons. And we'll talk about why that is. Other differences that you see, anybody? I think this is pretty much the list. So there are these kind of practical issues that ferromagnets are mostly metals, ferroelectrics have to be insulated. There's this chemical issue that ferroelectrics are mostly oxides, whereas in oxides we tend to have, if we have any magnetism, it tends to be anti-ferromagnetic. And then this issue that I want to discuss in a bit more detail is why, if I have a D0 cation, does it have a tendency to be ferroelectric, whereas a partially occupied magnetic cation with some d electrons has a tendency not to be ferroelectric. So that I'll go through in some detail. Questions? Anything else to add? Did any of you not have a class in perturbation theory? Okay, good. So what we're going to do is perturbation theory. I heard some blocks. We're going to do a little bit of perturbation theory to understand when a material will become ferroelectric or not. So we're going to start with the centrosymmetric arrangement of ions and look at whether making a ferroelectric distortion is going to lower or raise the energy. And we'll do that using perturbation theory. Okay, so we'll take as our zeroth order state a centrosymmetric arrangement of ions, and then see when we make a distortion whether the energy goes up or down. And if the energy goes down when we make a polar distortion, then our system wants to be ferroelectric. If the energy goes up, then it wants to not be ferroelectric. And what we'll see is that we can then understand why D0 cations want to be ferroelectric, whereas partially filled D shell cations won't be ferroelectric. So that's where we're headed. And I'm going to use the board, so you have to take notes if you want to have this. Keep this.
Can you please close that the blinds over there, because they have a
It's
reflection.
difficult to see. I've got the lights on the board.
Yes,
You know, in
yeah.
Switzerland,
Thank you.
just do we have any Swiss here? Okay, in Switzerland, the students clean the blackboard for you during class. so if they run out of space, I expect you to run that. But actually, also in Switzerland, they wash the blackboard. You don't just wipe it. It's really great. This is really, having taught in California for 20 years, it's really astonishing. I still can't get used to it. Are you from which university? Are you? Did they clean the blackboard in Geneva also, or just the ETH? Just in Zurich. Okay, just in the German part. Okay, so we're going to apply perturbation theory. To ferroelectric distortion. Can you see this? I actually can't see it at all. I can just see glowing on the blackboard.
Yeah, I think yes.
All I see is reflection. I don't know. Maybe if we put off the one that's blaring at the board.
Is it
This is the best. I could try color. Maybe if the color could reflect light.
Is that better?
Yeah, that's
This
perfect.
one is better.
This is fine for us. Can you see it on board?
Actually, this is better for me also, I think.
This looks good.
Is it good? Yeah. Let me try and see if this color is different. Is this better or worse?
Indifferent.
Indifferent. Okay. So what we're going to do is start from an initial ion configuration that's centrosymmetric. And let me just sketch in one dimension what I mean. This would really be a three-dimensional system, but for example, I might have, say, oxygen 2-, titanium 4+, oxygen 2-, titanium 4+. So if I had to say barium titanate is my ferroelectric. And at the start, these are going to be equally spaced, and I'm going to ask myself the question, are they going to distort and become ferroelectric? But this would be true. And I'm not going to take the time to work through explicitly the perturbation theory. I'm just going to kind of write down the answers, the steps. And if you've not had a perturbation theory class, you can just believe me that this is how it works. But we'll see how when we apply perturbation theory to this question, we'll be able to understand whether this will become ferroelectric. So we're going to solve the Schrodinger equation for this arrangement, for this, as we call this, the zeroth order Hamiltonian. So my unperturbed problem, we call it H0. My unperturbed problem is a centrosymmetric arrangement of ions. And when I solve the Schrodinger equation, this is going to give me the energies. E0 is the ground state energy of the unperturbed Hamiltonian. So this 0 is the ground state. And this 0 up here means it's the unperturbed Hamiltonian. The energy of the unperturbed Hamiltonian. And then I'll get, of course, all the excited states, and 1, 0, 2, 0, and so on. So these are the excited states. So this is just normal, how I normally proceed, and I'm going to assume I can do that. I can solve my Schrodinger equation for the unperturbed Hamiltonian, and I also get the electronic wave functions. Questions, or can you not see? Not clear?
Yeah.
Is the white because it's better?
Yeah.
Right. That says electronic wave functions. Psi 0, psi 1, the wave function of the first excited state, and so on. I think we're going to have real trouble when I've erased everything we started in. So that's the first step in my perturbation theory. I know the answer to the unperturbed state. Now I'm going to perturb the atoms, so step 2. Perturb them because it's perturbation theory. By moving them some small distance, it has to be a small perturbation. And we're going to call the perturbation Q. Along the ferroelectric distortion. If I would be to be precise, I'd say along the normal coordinate, along the pattern of atomic displacements that forms the ferroelectric distortion. And in the one-dimensional case, this is just the Q is just the distance that the titanium atom moves off center. Ion moves off center. If I was doing this really for three-dimensional barium titanate, it would be the pattern of barium and oxygen and titanium ion motions that takes me to the ferroelectric ground state. But in this case, oops, this is Q. My titanium is moved from this position by this amount. And now what we want to do is calculate the energy of this situation and see if the energy's gone up or down, right? That's what we're looking at. Questions? Okay, so the way that we calculate this energy then is perturbation theory. So, and what we're going to do is expand the new Hamiltonian. Let me just write that as H. As a Taylor series in Q. Q is small, so we're allowed to expand it as a Taylor series around the 0 point Hamiltonian. So our Hamiltonian is changing just a little bit, so we could write it down as an expansion. And when I do that, so my new Hamiltonian is the original Hamiltonian plus, and this is just mathematics, just writing down the Taylor series, dH by dq. If q is equal to 0 times q plus a half d2h dq squared. If q is equal to 0 times q squared, and so on. So there I've just written down a Taylor expansion. Okay, questions so far? So these terms change in the Hamiltonian, these capture any change in the nuclear or the ion-ion energies as I move the atoms, and any change in the electron-ion rearrangements as I move the atoms. These will all be captured by these terms. And so often they're called vibronic coupling. You hear the term vibronic coupling to describe how the energy changes, how the electrons rearrange and the energy changes as I move the ions. Okay. So now, this is our new Hamiltonian, and we move the ions. What we want to know is the energy. We want to know whether this energy is going up or down. And so I'm going to write down the answer then, which those of you who had a perturbation theory class could also do yourselves. So we're going to calculate the energy of the distorted system. Using perturbation theory, and we're going to stop at second order. And this, if I were to work it out, would be a couple of pages of algebra to go from here to here, but it's just exactly straightforward perturbation theory. So I'm just going to write down the answer for you. There's no new physics, it's just manipulating the mathematics. What we find is that the energy is the zeroth order ground state energy of the unperturbed system. So this is just the ground state energy of the undistorted system. Plus a first order correction to the energy. Is everybody happy if I use this bracket notation, or is anybody unfamiliar with bracket notation? Okay, I'll ask the question two ways around. Would anybody rather I didn't use bracket notation and wrote out big integrals instead? Okay. I asked the question though, if anyone's sleeping, I get the answer. Okay, so I have a first order term, which looks like this. So this is my first order correction to the energy. And this is the expectation value of our zeroth order wave function, zeroth order ground state wave function, in the first order perturbation to the Hamiltonian. So that's the first correction that I get to the energy. And then let me write down, and this one is not going to turn out to be relevant for ferroelectrics. We'll come back to that in a second. And then here's my second order terms. Can you see if I write here, or is the table on the right? It's fine. So then I have two second order terms. One with the first order wave function and the second order perturbation to the Hamiltonian. This one's positive. Notice, so positive is bad. If I want to become ferroelectric, positive is going to increase the energy, so this term is going to disfavor ferroelectricity. And then the second term, this one's negative, this is good. And this one looks a bit more complicated, but it's the term that has the first order correction to the Hamiltonian combined with the first order correction to the wave functions. That's why it ends up looking a bit complicated. So it looks like this, and don't worry, again, this would just drop straight out of perturbation theory. You work through matching all your terms and keeping track of everything. Q squared divided by EK 0 minus E 0. Okay, so in this term, the psi k's of 0 now are the excited states of the unperturbed Hamiltonian. and they have energy EK of 0. Okay, so this is the answer. I'll let you all finish writing, then we'll talk about what it means in terms of trying to become ferroelectric.
Sorry, the
Yeah.
summation is over the whole term, right? Not only over the upper part.
Yeah, sorry, the summation over the whole thing. And there's nothing exotic in getting to here. This is just really straightforward algebra, but I don't want to invest the time in that. We'll take our time talking about this. Any questions?
What is written down there on the right? Excited states of unperturbed?
Oh, I'm sorry. Yeah, from that angle you can't see. So this is psi k, subscript k, superscript 0. These are the excited states of the unperturbed Hamiltonian, and their energies are E subscript k, superscript 0. So the superscript means it's unperturbed, it's a wave function of the unperturbed Hamiltonian, and the subscript, because it's a k, not a 0, means it's an excited state. Okay, so now let's look at what this tells us about whether something's going to be ferroelectric or not. I think what I'll do is I'll take a colour and write them in there, because I think we won't see anything if I start running a video. Other questions? Yes?
So in your specific case, there is no degeneracy in the ground?
There's no degenerate, so I'm going to ignore degenerate ground states. Well, I'll mention it very briefly. Yeah. So this is, one can include degenerate ground states, but let me just keep it simple and assume that we have no degenerate ground states, just to make life easier. Psi here can be the full many-body, in principle psi is the full many-body wave function, although in a minute we're going to cheat and think in terms of just single particle wave functions because it's easier for the human brain, I think, but it's really the full many particle wave function for a solid. It's probably non-degenerate, or can be non-degenerate. Okay, so let's have a look at this first term. This is the first order correction in perturbation theory. The Hamiltonian of a system is totally symmetric, and Q, the distortion that we're making here, is a polar distortion. It has odd symmetry. My zeroth order wave functions are also totally symmetric. So here I'm making an integral over a product of two even things and an odd thing. So what happens if I integrate over all space a function that's overall odd, that has odd symmetry? It goes to 0. So for the case of Q odd, provided I don't have subtleties like degeneracies, this term goes to 0. So for ferroelectric distortions, I don't have to consider this further. This is the term that's important if you have degenerate ground states and you make an even distortion, and this gives you the first order Jahn-Teller effect. So this gives you, for example, if you have a perovskite with 4 d electrons, manganese 3+, for example, it gives you the Jahn-Teller distortion. So this gives you the regular Jahn-Teller distortion, but it's always a centrosymmetric distortion, and so it doesn't give you a ferroelectric. So that term we don't care about. These two terms down here, these second order terms, these are going to determine whether something is ferroelectric. So let's think about what they both mean. So first of all, these have opposite signs. So the second order terms. Can you see the pink? No? I think we're not going to see the white either. Can you see the white?
Yes.
Yes? Okay. I thought it would be worse because we're writing white on white. So these decide whether my system is ferroelectric or not. So the first thing to notice is they have opposite signs. So whether something is ferroelectric or not is a competition between these two terms. It's not a fundamental symmetry requirement like the first order Young-Taylor effect. In the first order Young-Taylor we have only one term. It's 0 or not. So whether something's going to be ferroelectric or not is a competition between two terms. So the two terms have opposite sign, and their competition decides whether something's ferroelectric. The first term is bad for ferroelectricity, the second term is good. Question?
Is there a significance that why this term is negative between the third and the fourth term, or is it just by rigorous algebraic calculations that you get it into negative? Because I can imagine that you are expanding in Taylor series, the whole Hamiltonian, and similarly you have to also expand, like if it is H psi equal to E psi, then you have to also expand the psi and also expand the energy eigenvalue. So then, from where this negative term is coming, is it possible to explain in short, or else I'll just check it in Griffiths?
Yeah, check it in Griffiths. But I guess so you can write it as positive if you like, but then you have to reverse on the denominator.
Okay.
And so then you would have E0 minus EK.
Right.
But remember, EK are the excited states and E0 are the ground states. And so, so this denominator, as I've written it, is positive. So this bit, if you like, is now positive with the minus sign out here. And so that just comes out mathematically. If
So basically, since you're distorting from the mean free energy, like so from the mean state, that is E00 to EK0, so then that is negative, getting into negative.
For this term, yeah, maybe it'll become clear when we talk about what this term means, or why this is then negative. Yeah, good question though. But mathematically, when you write it this way, it comes out negative. I can tell you why in my simple chemist's explanation why this is an energy low. Maybe your question is why is this an energy lowering term? Yeah, we'll talk about that. Okay, so this term is energy raising. So let's think about what this means. Here, we're taking the expectation value of the second derivative of the Hamiltonian. So if you like, the kind of curvature of the energy as a function of displacement, right? It's, as I push my atoms together, they're following some energy well. But I'm not letting my wave functions move. Right? These are my zeroth order wave functions. My electrons are not allowed to move. They're not allowed to adjust to the fact I've pushed the titanium towards the oxygen. And so we know from the variational principle that's got to increase the energy, right? Because I've solved my zeroth order Hamiltonian, my zeroth order Schrödinger equation, I found the energy ground state, and then keeping the electrons stuck in that energy ground state, and I'm changing the Hamiltonian. So that would be the same as keeping the Hamiltonian the same and changing the electrons away from the ground state. I'm making the electrons be the ground state for the wrong Hamiltonian. So this raises the energy. So conceptually we can see that why this has to be positive. This has to raise the energy. I'm moving the atoms and I'm not letting the electrons adjust. So the first term is the energy cost of moving the ions without letting the electrons adjust. So it doesn't allow for any chemistry, it doesn't allow for any covalency. All I have is the Coulomb repulsion between those frozen electrons as I push my atoms together. Okay? So it captures the repulsive forces, which are Coulombic, because I'm not letting any covalency happen. Repulsive Coulombic forces between the electrons as the ions are displaced. Between electrons as the ions are displaced. Okay, everybody happy conceptually with that?
Yep.
So immediately I can start to see why these, or start to think why these Dn transitional metal atoms are not going to be good for ferroelectricity. If I have a lot of valence electrons, then this term is going to be larger, right? I can minimize this term by having as few as possible electrons in the valence. So for a D0 cation, of course this term will still be positive. There's still an energy cost of pushing a D0 cation towards an oxygen and not letting the electrons adjust. But it's going to be less costly than if I have a lot of valence electrons there. So this term is minimized for few valence electrons. I get less Coulomb repulsion between the electrons and the ions if there's less electrons there. Now, of course, this is a little bit hand-wavy, but it's the right. I'm not lying to you. So already this is pointing us in the direction that D0 is going to be good for ferroelectricity and Dn is not. Okay, questions on this term? Let's look at the second term one. This one's a little bit more subtle. What I first want to look at is when this second term is large and when it's zero by symmetry. So the second term, remember, I would like to be large. Oops. Second term is negative, the way I've written it. So the second term favors ferroelectricity. We want this to be large if we want a ferroelectric. Okay, so if we first look at the denominator, when's it going to be large? The denominator is small, right? So we'd like to have low-lying excited states. Okay, so it's large when for low-lying excited states. So it's large when EK minus E0 is small. So it's only really going to be, this term's really, we only really have to think about this term for the low-lying excited states. The really highly excited states, it doesn't really matter because it's going to be very small. Let's do the symmetry argument thing again, though. So dH by dq, we decided is odd. The ground state is going to be totally symmetric. In order for this to be non-zero, the excited state has to be odd. Yeah, the excited state has to be odd, right? For this integral to be non-zero. So if we say the ground state is even, dH by dq is odd for an odd perturbation, then the excited state should be odd for small k, for low-lying excited states. For k small, I mean low-lying excited states. Just by symmetry. Okay. So if this term is going to be negative enough, we need to have the numerator non-zero when for low-lying excited states. So this doesn't tell us anything yet formally about D0 or not. But when we think about, we're going to look next at some band structures, and we'll see that for transition metal oxides with D0 cations, this is fulfilled for the low-lying excited states. So we'll look at that next. Questions yet about the symmetry argument or the mathematics? Okay. Let me sketch for you. Oh, and yeah, maybe we should also just talk about what this term means. This term is capturing the relaxation of the electronic wave functions as the ion is displaced, right? It's because this psi k of 0, actually this whole summation, if you remember your perturbation theory, we could rewrite this actually as psi 0 dH by dq psi 1. Yeah, where this would be the first order corrections to the wave functions. If you don't remember that from perturbation theory, don't worry about it. But this is capturing, as I move the ions, how the electrons then relax to accommodate the fact that their Hamiltonian has changed. And that's why this term is negative. It's an energy lowering process that the electrons perform after the ions have been shifted. Okay. Would you like to sketch in your notebooks the density of states of barium titanate, or would you rather I did it? Okay, let me do it, just in the interest of time. Okay, if we look at the density of states as a function of energy for barium titanate, and it's just very simple. Here's the Fermi energy. These are the oxygen 2p states. The oxygen 2 minus ion is completely filled. And here's the titanium 3d states. And this is the Fermi energy. So that's how the density states of barium titanate looks. So in my zero-order wave function, all my electrons are in the oxygen 2p states. I have a completely full band. It's a totally symmetric wave function. So psi 0, 0 is symmetric. And now I make my first excited state. I take an electron out of the oxygen 2p band and I put it in a titanium 3d. So now I have taken out an odd electron, if you like, and put it into an even state. Right? My 2p orbital was odd, my 3d orbital is even. So my first excited state, psi 1, 0, is odd. So for barium titanate, or for any, sorry, I should have written this is density states of barium titanate. Any D0 transition metal oxide, the numerator is non-zero for the lowest excited states. So my numerator in the second term is non-zero. And the ferroelectricity wins. Or wins in quotes, because it's not really a competition. So the second term is large and negative because of the d-zeroness, because the conduction band has d symmetry, the valence band has p symmetry, these have different parities, and so the first excited state in this case is odd. I hear this kind of silence. Is it really confusing or like really obvious? What on earth is going on about? Questions? Yeah.
So we can apply this principle to all perovskite selector since we have TeO6.
So, I mean, this principle you can apply to, if you like, to anything.
This electronic structure, for example.
This electronic structure? Yeah, this is the electronic structure of, simplistically, it's the electronic structure of any D0 perovskite, right? So barium titanate, lithium niobate, lead zirconate, then you have the valence band is made primarily of oxygen 2p, and the conduction band of empty D state. I'll show you some real electronic structures at the moment. You'll see that's a little bit simplistic, but basically that's the density of state of any perovskite. Questions? Yeah.
So it seems like a large gap will suppress ferroelectricity. It's like, would a semiconductor maybe help ferroelectricity?
So if the gap is, by this picture,
I mean, if you have the right symmetry and everything.
If the gap is smaller, then this term will be larger. Of course, if you have small gap, then you have lots of other problems like leakage, right? That, for example, germanium telluride is a very small gap and very good, has a very large ferroelectric polarization. But yeah, that's a good point. I guess that the gap needs to be, so again, it's a competition, right? It's a balance.
If the coercive field ends up exciting or making it metallic, then
it's no good, right? Yeah. So probably designing your ferroelectric by looking for the smallest gap would not be the smartest way to do it. Okay, let's do this same exercise now for a non-D0 perovskite. Say a Mott insulating perovskite. I want to leave let me just erase this bit, sorry. And then we'll move on to look at some multiferroics. So I'm going to pick an insulator so I don't have the problem of being metallic. Let's look at a typical kind of Mott insulator perovskite, calcium manganite.
Excuse me?
Yep.
One question. So I see with your symmetry arguments that the second term is non-zero.
Yep.
But what is the argument that it's added to the first term still below?
That it becomes larger? It's a really good question. So I've not made an argument of that it should win. It has the chance to win because it's non-zero, right? So you have this negative term. But this is a really good question. Think about, for example, so barium titanate, our favorite ferroelectric. What about strontium titanate? Ferroelectric or not?
Yes.
No, it's not, but it's really close to being ferroelectric, right? It wants to be ferroelectric. But in strontium titanate, so it has the same, basically the same chemistry as barium titanate. If I were to draw the band structure, it would look identical to this, right? Strontium titanate. This term is still negative, but the balance between them is just slightly such that the first term wins. Ever so slightly. At 0 Kelvin, it knows that it should become ferroelectric. So all we're looking at here, if you like, is whether there's this propensity to become ferroelectric. It's still possible to really know which one's going to win. I think there's no way intuitively you could say finally for sure. We can say, okay, it's likely if something's D0 that it has the tendency to become ferroelectric. And we know that strontium titanate has that tendency. It's a very good dielectric, but it doesn't quite make it. And the reason, as I think of it, is the lattice constant is too small in strontium titanate. So this term gets bigger. Your eyes are already close together. You try pushing them together, and the energy goes up more. So in strontium titanate, these terms are exactly balanced. Okay, very good question.
So is it possible to disturb the balance of strontium titanate by integrating it with a very highly metallic system like graphene or 2D materials?
I'm not sure about graphene. I'm sure it's been done, but when you strain strontium titanate, for example, it does become ferroelectric. When you dope it with a little bit of calcium, it also becomes ferroelectric. That's very interesting. I think it's not understood. It's believed maybe the calcium's so small it rattles a bit and kind of just drags everything else along with it. But it's so close to the boundary that anything you do to strontium titanate can make it be ferroelectric. Does anybody know strontium titanate on graphene? I'm sure it's been done. It's probably superconducting. Yes, but I don't know if it becomes ferroelectric. Do you know? Is it something you're working on?
Only the surface dipole, so on the surface is, the salt on the surface is ferroelectric. There is no demonstration that STO is totally become ferroelectric.
Okay, but the surface becomes polar on graphene. Okay, very interesting. Yeah, it's a good question. Also, we can discuss that question in the context of calcium manganite also. So calcium manganite is the Mott insulator. So if we draw the density of states now, it's manganese 4 plus, so it's D3. There's 3 D electrons. And so the band structure, of course, there's still this oxygen 2p band. The oxygens are still oxygen 2 minus, but the band structure has the T2G, the manganese 3D T2Gs, sitting at the Fermi energy. And then above the Fermi energy now are the manganese 3D EGs, EG orbitals. Oops. So now 2 things. First thing is the first term's bigger. I have this cloud, this spherical cloud of d electrons on my manganese, and I try and push it towards the oxygen, it gets pushed back more. So the first term, the positive term, is bigger because of the of the 3D3 kind of cloud with electrons. Questions? And then the second term, now I take my electron from the top of the valence band. It has d symmetry, has even symmetry, and I put it into the bottom of the EG band, into the bottom of the conduction band, which is also a d state with E symmetry. So the second term, the numerator goes to 0 in the case when the denominator is, in the case where the denominator is small. So in the second term, goes to 0 for small ek minus 0. So calcium manganite is not a ferroelectric. The balance between these two terms, in the case of a partially occupied P shell, means that it tends to not be ferroelectric. Now again, it's a balance between these two terms. So it's not the case that calcium manganite is not allowed to be ferroelectric. And in fact, if you strain it, at least in the computer, it becomes ferroelectric. I don't think this has been done in experiment. Does anybody know? But when I strain calcium manganite in my computer, I can make it ferroelectric. Because I can tip the balance between these terms. Essentially, when I strain it, I elongate along one axis, and I make this term be smaller, because I make the axis longer, and so I get less Coulomb repulsion when I push the ions towards each other. But the balance for just the regular material means that it tends to not be ferroelectric. But of course it is magnetic. It's an antiferromagnet. So it's not ferroelectric. But it can be magnetic. It's not a ferromagnet in this case, but it has local moments, so it's an antiferromagnet. Okay, questions?
Yes, because actually here the second term goes to 0, but if the denominator is larger.
Yeah, so certainly, so again, this is a balance. So by the time I get down to these states, when I get deeper into the valence band and I'm taking an electron out of the oxygen 2p and putting it into the conduction band, then the term becomes non-zero. Yeah, is that what you're thinking? So
there is written that is small.
If it's large, then you have to write symmetry.
for small denominator,
Yeah.
oh, you're right. The second term is non-zero. The second term is 0. When the denominator is small. So when the denominator is small, when I make the excitations directly across the gap, which would make the term large, then it goes to 0 by symmetry.
Okay.
Okay, yeah, so I think it's written the right way around.
Okay.
Is that right?
It's correct.
Okay. I don't know how many of you are teaching a lot, but your IQ drops about 1 million percentage points when you're there's not that many percentage points to drop, but it does drop. Okay, other questions? Yep.
It hasn't so much to do with the thing, but I'm a bit confused by the term mod insulator to begin with, because here in this case, I mean, the insulating state comes just from the fact that there's a crystal field split in.
Yeah, okay. I also hate this term, mod insulator. Let me say instead an insulator with a DD gap.
Okay.
Yeah, okay. I also personally think that calcium manganite is not a mod insulator.
At least a lot of perovskites turn out.
Yeah, but this is a huge discussion we can have over a beer, maybe a big philosophical discussion about when is a mod insulator not a mod insulator. An insulator with a DD gap. My expertise is electronic structure calculations with density functional theory, and so I'm very unhappy with the idea of anything being a mod insulator because I can't capture mod insulating behavior within the tools that I have available. So I try to fool myself that there's nothing that Mod insulators don't exist, but I completely agree with you. I personally don't think that calcium manganate is a mod insulator. But it does have a DD gap. Yeah. Okay, other questions? Okay, how are we doing for time? Can I have till about 20 past and you still make it for lunch? Because we started like 15 minutes late. Oh, one last thing though. This is called the second order Jahn-Teller effect. So you'll hear this term quite a lot. Don't get it mixed up with the regular Jahn-Teller effect, which is the one that tells you that lanthanum manganite has a distortion among its d electrons. This is the second order Jahn-Teller effect. Because it's coming from the second order perturbation theory. It's an effect, not a theorem, because it's a competition. You don't say, okay, I'm D0, I must be ferroelectric. I'm D0, so I have a chance to be ferroelectric. I'm D3, so it's difficult for me to be ferroelectric. It's a competition between these two terms. Okay. So all of these reasons we've discussed,
Second order Jahn-Teller when ferroelectricity wins or loses, or
the whole thing is called the second order
okay,
Jahn-Teller
this
effect.
competition.
It's competition.
Okay.
Okay. So that we did perturbation theory. Blah, 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 blah. Okay, so here's the real density of states then, or real calculated with density functional theory. This is for barium titanate in the centrosymmetric structure. Maybe if I can get rid of that little mute symbol on that. And the top is the calculated density of states as a function of energy for barium titanate in its centrosymmetric structure. So this will be like our H0. You see the valence band, this is the oxygen states. The valence band is mostly oxygen. On the top is the titanium states. The conduction band is mostly titanium. This line is the Fermi energy. When we say that titanium is D0, then we're kind of lying. It's titanium 4+, so formally it's D0. But if you look at the density of states, there's actually rather quite some electron density on the titanium already, even in the centrosymmetric state. In the bottom, look at what happens now when I displace the titanium towards the oxygen. So here's the Fermi energy again. I want you to notice these states now down at the bottom of the valence band, or how the bottom of the valence band is shifted down by almost 2 electron volts. And there's a band here in the density of states that has a lot of titanium ions, mostly titanium Z squared. I moved the oxygen in the Z direction in this case, and a lot of oxygen. And whenever you have these very strongly overlapping densities of states, this is a sign of chemical hybridization, usually covalent bond formation. So this, if you like to think of a kind of chemical picture, this bond formation between the titanium and the oxygen is what drives the ferroelectricity in barium titanate, what lowers the energy. If I look at calcium manganate rather, actually I didn't show you the oxygen states here, sorry, I should have done. This is the density of states of the manganese in the centrosymmetric structure. And when I displace the manganese towards the oxygen, I can do this in my computer. I can make calcium manganate be ferroelectric just by moving the manganese atom. Of course, it raises the energy, but I can do it. Then you see I don't get this energy lowering at the bottom of the valence band. I don't really get much of a shift in the density of states. There's not much chemical bond formation. All I get is the increase in energy from pushing the ions together. So that's how it looks like kind of in real life. Okay, so the reason, there are many reasons that we've already discussed why there are so few magnetic ferroelectrics, that a magnet likes to be metallic, a ferroelectric likes to be insulating. But what we've gone through in detail then is that the chemistry that promotes one functionality often prohibits the other. So for ferromagnetism, one wants to have partially filled d orbitals, rather localized partially filled d orbitals. For ferroelectricity, one wants these empty d orbitals because you have this competition between covalency and Coulomb repulsion. And this was known millions of years ago. So when I dug this out, I heard somebody called the Matthias rule. So Ben Matthias, in 1949, pointed out that all of the ferroelectric crystals that were being discovered back then had this D0 feature. I guess he didn't really understand why, but if you want to look to make a new ferroelectric, look for something with empty field. Okay. Questions? Let me see. So, I think this will largely cover next time, but just let me get started on it. So if I want to make a multiferroic, if I want to combine magnetism and polarization, then I should either use an alternative mechanism for the polarization, not put in a D0, not rely on having a D0 transition metal cation, because then I can't be magnetic. Or I should use an alternative mechanism for the magnetization. I should introduce my magnetism somewhere else, not on the transition metal d electrons. If I want my transition metal to be ferroelectric. I don't know if last week did Philippe Gauzet, I think he said he was going to talk about competing instabilities in complex oxides, did he? Anybody remember that far ahead? So another approach, and I'm not sure if Philippe addressed this, but you can think about how could I tip the balance in the second order Jahn-Teller effect? How could I reduce the Coulomb repulsion and enhance this chemical covalency, maybe by strain or by somehow disabling the rotations I think Philippe will have talked about. So this is also another approach, kind of tricking the energy balance in the second order. So most of what I'll cover next time then is how we can introduce in a conventional transition metal oxide where the magnetism is coming from the 3D transition metal electrons, how can I trick the material into being ferroelectric? So let me show you, I think what I'll do now, and then we'll stop after this because in the interest of you getting your lunch, is just go quickly through this zoology of multiferroics that we know about now, in which the ferroelectricity is coming from an unconventional mechanism. Unconventional in the sense that it's not D0-ness on the transition metal. So it's not like barium titanate ferroelectricity. Okay, so the first trick is using what's called a stereochemically active lone pair. And this happens, I know that I heard many of you say you're working on bismuth iron oxide. This is what happens in bismuth ferrite. The iron, of course, is magnetic. It has 5 3D electrons, so it doesn't like to be ferroelectric. But the bismuth has what's called a lone pair of electrons. And this, you're familiar with, I know, from your introductory chemistry classes, when you look at the stereochemistry of ammonia. So this is an ammonia molecule, NH3. If we just naively thought NH3 and tried to write down the structure, we'd think of ammonia as being trigonal planar, right? The hydrogens should spread themselves out and it would be a plane. But the nitrogen has a lone pair of electrons, this little yellow umbrella, and that occupies space and it pushes away the hydrogen atoms. So the reason that the ammonia molecule has a dipole moment, this is negative, the hydrogens are positive, the ammonia has a dipole moment, is because of this, it's called stereochemically active lone pair. It's a pair of chemical electrons that takes space. So this is exactly the same chemistry that makes bismuth iron oxide and bismuth manganite bismuth iron oxide is ferroelectric, bismuth manganite is actually anti-ferroelectric. But they develop these local dipole moments. So this is one trick. We'll talk about that in a bit more detail tomorrow. Another trick, this is I think really, really elegant. This is my favorite mechanism for making a multiferroic. If one takes just a centrosymmetric crystal structure and arranges the magnetic moments so that they break inversion symmetry. So if we look at this crystal structure and say these are my cations, this is just a schematic, then without the little arrows, this material would have an inversion center. If I sat at this point here, then I'm exactly the same top left, bottom right, and top right, bottom left. This would be an inversion center. So it would not be ferroelectric. If my system has an inversion center, it can't be ferroelectric. But for this particular magnetic ground state, which is a spiral of the spins, when I sit here, if I look up and left and down and right, I see something different because the magnetic moments are different. So the arrangement of the magnetic moments breaks the inversion center When the inversion center is broken, then I'm allowed to have a ferroelectric polarization. So this is very beautiful. This is my favorite mechanism, because the polarization is only there because of the magnetism. So they're completely coupled. This was actually discovered by Bob Noonan and Eric Cross that Beatrice mentioned earlier in 1978, where they identified this magnetoferroelectricity in chromium chrysoberyl. They have a beautiful quote in this paper. It says, magnetic ferroelectrics might therefore be termed the ultimate improprietary, which is usually, it's such a funny word. How many of you are native English speakers? It's a kind of word, I don't know what you think of impropriety. It's like if somebody's behaving inappropriately at an elegant dinner party. You say this is an impropriety. So they said this is a multiferroic cell. I don't know why, it's very, very cute. Another mechanism which is also very, very clever is charge ordering. So this was first identified in lutetium iron oxide. It's also now proposed for magnetite. If I have an arrangement of ions which is again centrosymmetric, and then I have a charge ordering. So for example, in lutetium iron oxide below a certain temperature, the electrons localize and make separately ion 2 plus and ion 3 plus ions. And before that happens, the lutetium iron oxide is centrosymmetric. But now if you look at the schematic, there's stripes of ion 2 plus ions and stripes of ion 3 plus ions, so the inversion center is lifted. So by ordering the electrons, by this charge ordering mechanism, one can make a ferroelectric. And then the last example that I'll discuss next time in a bit more detail is what's called geometric ferroelectricity. And in this case, the centrosymmetric structure has the cubes kind of all perfectly lined up. And this particular material is not an oxide, actually, although this does also happen in oxides, nickel fluoride. The structure has this rotational instability, and the rotations are also polar. So as this material rotates, it pushes the cations out of the way and makes an electric polarization. So we'll talk about these four in a little bit more detail next time. But let me stop there for now so that you don't miss your lunch, and if there's time, I can take questions now or over the lunchtime.